So benzyne is a useful synthetic intermediate that can be generated from dehydrohalogenation of an aromatic bromide. So here I have an aromatic bromide, and if I treat this with a strong base, sodamide is a common base, so NH2 minus with either sodium or potassium counterion. What happens is wind up doing this elimination of HBr to give the benzyne intermediate. So now you're looking at this and saying that's a triple bond in an aromatic ring that looks really funky, that looks really strained. It's really not a strained system. What it is, we have the groups from the pi ring, and I'll draw those out in red. So we have all these p orbitals that are lined up for the aromatic ring, and they're all delocalized, and perpendicular to them we have orbitals that contain the single electrons for that extra bond of the benzyne. And it could be drawn as a single radical, or we could have a situation where there's both electrons on one side for a negative charge, and this side would be the positive charge. This would be a possible resonance structure. And then the other option is where the other side is positively charged and the other side has the two electrons, and that's negatively charged. So benzyne functions as an electrophile. And we'll see that on the next slide. Okay, so again, I have shown the reaction to form the benzyne, and what I've done is I've shown it with a radio-labeled carbon. So this is carbon 14. It's a way of tracking where the incoming group goes on the benzyne intermediate. So you would think if it was just a simple displacement of the chlorine with the sodamide, because the next reaction that happens is reaction with the NH2 minus, and this attacks, and we wind up with again, this is the radio-labeled carbon, and the nitrogen adds in on this side, and this is a negative charge. But we also get the same addition where it adds to the other carbon, the one that's the radio-labeled carbon. And this carbon has the negative charge. And then just treat this with a proton or acid to work it up. You wind up with both isomers of the radio-labeled compound. Where that nitrogen is either on it or next to it. So if it was just a simple SN2 displacement or some kind of displacement, we would only get reaction of the sodamide, the nitrogen attacking at the same carbon. The fact that we see both of them gives us this intermediate where both sides are equal to each other in the benzyne, and attack could occur at either carbon. Okay. So again, here's that picture of the perpendicular bonds to show the benzyne. Is those extra electrons are not within the pi system. Okay, so again, we talked about the reactivity. We think about nucleophiles reacting with benzyne since it's an electrophile, and it could attack at either carbon. So it could attack at this carbon or at this carbon. If you think about it, if it attacks at carbon 1, that would be from this resonance structure where that carbon is the positive charge. If it attacks that carbon 2, again, that would be this resonance structure where that plus charge is at this structure. All right, so using Benzyne becomes more interesting when we have more than just a single group on it. So I'm going to do some Benzyne reactions of some aromatic compounds. Just give me a second to draw them out. So what I'm going to do is I'm going to take this bromide, the meta, and the para bromo. So forming Benzyne with this one, I only have one hydrogen that I'm able to remove. So if I treat this with sodamide, what I wind up with is a single Benzyne intermediate, which is going to look like this. All right? So there's only one possible Benzyne intermediate. And then when I do the addition of another equivalent of sodamide, it could either add at this site or add at this site. And that's going to give me two possible products for this one, where I have the NH2 here, and the other one where I have the NH2 on the other side. Okay. With this one, I have two possibilities for Benzyne. I could remove this hydrogen, or I could remove this hydrogen, and that's going to lead to two separate Benzyne intermediates. So the first one, if I eliminate this hydrogen, that's going to give me the exact same Benzyne that I had in the first example, and I'm also going to get elimination this way, where I'll get this Benzyne. All right, so this one is obviously going to lead to the same two products that this one did, so I'll get both of those products. But this one actually introduces another one. I'll get the attack here or here, which adds to a different para product. So again, these two are going to be identical to each other. And this second Benzyne is also going to generate this one, but it'll also give me a third one to where I'll have the nitrogen para to the methyl group. So the first one gives me a single Benzyne, and I get two products. The second one gives me two different Benzynes, and I get a total of three products. For this one, both of these hydrogens are identical to each other, so there's only one possible Benzyne when I react this with sodamide, and that's going to give me this Benzyne intermediate, which is the same as this one. And again, that'll lead to the same two products. I could get attack here, or I can get attack here. So I'm going to wind up with this possibility after quench, and I'll also wind up with the para product after a quench. So just to go through this again, single Benzyne, because of the symmetry of the molecule, this one gives me two separate products. This one also gives me a single Benzyne intermediate and two possible products. This one actually gives me two Benzynes, the middle one, and I'll get three possible products from that.